It is a pleasure to welcome you to the third edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. The International Workshop on Unsaturated Soils was hosted in 2022 during the third edition of the AGERP lecture series. The following lecture on partial saturation influences on the characterization and strength of silty tailings was delivered by Professor Adrian Russell at this workshop. Adrian Russell is a professor in geotechnical engineering at UNSW Sydney. He is also an Australian Research Council Future Fellow. As a Future Fellow, he devotes 100% of his time to research on tailings liquefaction, having been relieved of his normal teaching and administration duties until mid-2025. His expertise is in laboratory element testing of soils and tailings, laboratory-controlled CPT and earthquake simulation, particle and pore geometry characterization, unsaturated soil mechanics and cavity expansion theory, and knowledge transfer to industry. His other research expertise includes applied unsaturated soil mechanics, the way unsaturated soils can be characterized using in situ tests like the CPT, and the way they interact with infrastructure, the modeling of soil behavior, linking microstructure to large-scale behavior, rock mechanics, focusing on failure mechanisms and microstructural deformation. He is an Australian representative on TC106 and TC221, which are international technical committees on unsaturated soil mechanics and tailings within the ISSMGE. He does expert review work on the stability of TSF. In 2019 he spent a 6-month secondment with Bell Sullivan Mining Proprietary Limited, providing expertise on mine waste projects. He was awarded his PhD in 2005 and BE in 1998, each by UNSW Sydney. His first academic appointment was a lectureship at the University of Bristol in the UK. This was followed by a move UNSW Sydney, where has been ever since.
Hello everybody, thank you for signing in. Look, thank you Partha and Satcham for this wonderful initiative, providing low cost, or in this case free seminars during COVID, when opportunities to interact with people and learn new things is a little bit limited. So look, it's an absolute pleasure. I'll be talking mainly about tailings and how to characterize them, mainly using the CPT, and a little bit about their strength. Tailings are obviously a soil-like material. I guess they're a little bit different to a natural soil in that they're very, very deep. We don't usually have a bedrock and interaction with a bedrock to worry about. And they're also silty usually, and they have this optimal particle size and pore size distribution that gives them one or two peculiar behaviors that we need to deal with in practice. And I'll talk about that. Look, a lot of the content relates to a large tailings research project I've been involved with, which is now just finished. It involved 4 universities plus 6 mining companies and the Australian Research Council. So a huge thank you to the funding provided by that. And I'm lucky enough, as Partha just mentioned, to be now on a future fellowship to do even more research on tailings over the next few years. So just outline the presentation. I'll just give a background and motivation for the work. And I'll talk a little bit about what we know for the CPT and unsaturated natural soils, including mainly sands and a decomposed granite. And I'll talk a little bit about the importance of the drainage condition and what suction does to that, in particular how it might change the soil's deformation around a cone tip. And I'll show some examples and applications. And then I'll focus a little bit more on tailings, CPT characterizations and their strength. And I'm really pleased the audience here is mostly people in industry. This talk is very much geared towards industry people. So I'll summarize it using graphics and key points that hopefully will resonate with people in industry, and they can take them away and try to use them in practice. So what are unsaturated soils and tailings? Just a little bit of background. There's a mixture of air and water in the pore space. They're widely encountered in slopes and dams and compacted soils, but in the mining sector as well, in ore, through transportation especially, or in tailings. So the air pressure is usually larger than the water pressure inside the pore space, made possible by the surface tension of the air-water interface. There's a capillary action, if you like. And we call the difference in those pressures suction, or matrix suction more accurately, but I'm going to talk generally about suction, which means that capillary phenomenon. And that pressure differential and the tension in the water literally pulls particles towards each other and increases the contact forces. And because soils, tailings are primarily frictional materials, that increase in contact force increases your friction angle or through an increase in the effective stress, or increases your frictional component, I should say, through an increase in the effective stress. So this is how we define the effective stress here. It's the total stress plus suction multiplied by chi. This is called the effective stress parameter. I'll put a little note down here in the bottom right. Chi is interchangeable with the ratio between tan phi b and tan phi if you want to refer and adopt slightly different notations and terminologies. They're one and the same. Everything is essentially transferable. And you just simply then can apply something like the Moore-Coulomb criterion to get your shear strength and so on. There's a second influence of suction through the friction angle. It might increase it by 2 to 6 degrees in some cases, but often we can ignore that, which is conservative to do so usually. And you capture most of the suction influences through the effective stress. So here's just a typical behavior that shows some of the peculiar things that suction can do to a soil in a triaxial test. I'll start with these first two simulations down the bottom. Deviatoric stress, these are samples on a decomposed granite, a well-graded silty sand. These first two simulations are for saturated, and the void ratio is around about 0.4. That's actually quite a loose state for this decomposed granite, even though it sounds like a low value. It's actually still causes the tailings, the soil to increase monotonically in strength, typical of a loose material, and exhibit volumetric compression as you do so in a drained state. Now, the next two simulations are for an even looser state. The void ratio is around 0.47, but now a constant suction is applied of either 100 or 200. And look at the huge enhancement of strength. Not only does the strength increase, but it now looks like a response typical of a dense material. You get a peak followed by a softening towards a large strain critical state value. So even though this material is looser, the fact that suction is present hardens the material and makes it feel as though it's somewhat over-consolidated and behaving like a dense material. We call this phenomenon suction hardening. Now, what is behind this is also a shift in the compression line, the isotropic compression line, if you like, or even geometric one as well. For the saturated state, you'll get sort of classic compression response. If we take a lot of stress, we can usually put it into some nice linear segments. But when it's unsaturated, that compression line shifts towards the right. And this controls the size of your yield surface if you're talking about a chem clay type material. So it actually makes the elastic domain bigger and the material harden or appear to be much stronger and more over-consolidated. There's a companion set of shifts of your critical state lines as well. So if this is your saturated normal consolidation line through here, and then for an unsaturated state, it's over here, your critical state lines also shift while maintaining a constant separation from your normal consolidation line. So your saturated critical state line will be this inner one here, and the unsaturated one would be over here. So this is how we extend the general critical state framework for an unsaturated material. And it helps us reproduce all these strange behaviors that we see on the left. Now, it's very important to incorporate water retention properties, or as Harriato spent a lot of time talking about the soil water characteristic curve. Tailings are not soil, so I'm calling it a water retention curve instead. But it's the same thing. It's that basic relationship between your degree of saturation and suction. And here I'm plotting everything using double log scales. And it so happens that nice straight lines generally tend to exist. And that's because there's a special property of the pore size distribution, which is fractal, meaning that you get these linearities in double log planes. But that water retention also enables us to at least determine with a pretty good accuracy and without direct measurement that the chi value that is important in our effective stress computations. So the dotted lines through here are our water retention lines. So we've got the other one here, which is called our main drying curve. So during a drying event, the state moves along that curve towards the right. And then if we wetted the material, it would move across a scanning curve and then onto the main wetting curve, and then rise in degree of saturation until you attain a value of 1 and the material becomes saturated. Those two intercepts with the degree of saturation of 1, we denote as air entry suction or air expulsion suction, depending on whether you're drying or wetting. The chi relationship is also a set of straight lines that has a compatibility to the water retention relationship. So during a drying process, this is your line down here. During wetting, you move along a scanning curve, and then upon further wetting, you end up on the main wetting part of that chi relationship. Straight lines in double log planes obey power laws. So here's our expression on the top right for our water retention or our degree of saturation as a function of suction. And likewise for our chi value, again, just a simple power law. So the exponents alpha is the slope of our drying and wetting curves, and the capital omega is the slope of our drying and wetting for the chi relationship. Now, there's a really important dependence on void ratio that we need to capture as well. Obviously, a looser material, a larger void ratio, has larger pores. Larger pores means that you need a smaller suction to overcome the capillary forces causing air to break into the material as you increase the suction, or and conversely during a wetting process when suction lets the degree of saturation become unity. Now we can capture that void ratio dependence in these simple power laws. For our air entry suction, it scales with void ratio raised to a power multiplied by a constant with units of stress. Now, air expulsion suction has the same power law dependency, but with another multiplier, C2, which just controls the horizontal separation between the two lines. These are not empirical lines just wished in for fun. These have a theoretical basis derived using the fractal geometry of the particle and pore size distributions. Air entry, air expulsion suctions really relate to the pore size distribution, but notice that as the capital DS, which is our power exponent, that is a property of the particle size distribution. It happens to be the fractal dimension of that particle size distribution. Here are some typical numbers up here on the right in the box. Omega is minus 0.55. Alpha ranges quite a bit more than omega between those numbers given, beta, and so on. And then the slopes of the scanning curves are interrelated through this relationship with the slopes of the main wetting and drying curves. As I said, ds is the fractal dimension of the particle size distribution, typically has a value between 2.2 and 2.8. The beauty of linearity in double log planes and these power laws is that you can easily interrelate and combine things and express them in terms of different parameters. So here's an expression for chi-s, which is a contribution of suction to effective stress, now expressed in terms of the gravimetric water content and void ratio, derived purely from this graphical presentation and all the equations that define it. And you can see all the power exponents are given there. And so now we can compute chi-s and understand how it changes with changes to moisture content or void ratio as well. Now, this is again more general content that is geared towards industry. I'm going to push the idea here that we can capture the effects of suction through what I've called the equivalent method. This is not entirely a new idea. Parts of it are, I'll explain in a second, but we can essentially use a software or a hand analysis without directly trying to capture suction influences and pore pressures, but instead just essentially do a total stress analysis, but with an equivalent cohesion defined as our saturated cohesion plus a part due to chi-S. Now, I must say that this has a theoretical basis. We did a whole lot of strength and stability analyses using slipline theory, slope problems, shallow footing problems, retaining wall problems, where our cohesion varied linearly with depth, according to this expression on the right up at the top, and our chi-S also varied linearly with depth. So the subscript 0 indicate values of the ground surface, and K subscript C or chi-S represent the variation with depth. So not only do we have to compute an equivalent cohesion when we do this, we also need to compute an equivalent unit weight. And this is something that's been largely overlooked in the literature until I did these analyses with my colleagues. But we need to also adjust our unit weight by capturing the variation of our cohesion or chi-S with depth as well. And just simply using those equivalent cohesions and unit weights means we can ignore all the other suction details of the stability problem and go straight to a software and essentially set all the pore pressure to 0 everywhere, and we get the correct result. And that's because we've preserved the dimensionless quantities which govern the physics of the problem. And I'll show an example of that in a minute. But generally, doing this in practice, we need to make sure that the chi-S profile that we use and define using this linear segment is representative of the worst case scenario. So this will usually involve a wetting process or perhaps even be when the hydraulic state is on the main wetting curve. And we don't need to go to the inbuilt features in the software which require unsaturated soil properties that might be a little bit too hard for us to understand and derive. Now, this approach is perfectly valid when chi-S doesn't change a lot during deformation and leading up to failure of our structure. And this is generally true when our degree of saturation is less than about 0.5 for slow and fast loading situations. Now, I'll give some evidence for that in a minute, but it's also true when our degree of saturation is any number, as long as we've got slow drained loading situations all the time. So here's that example that I promised using the equivalent method. This is something we teach our students at UNSW in Sydney. So for a slope problem, the dimensionless groups which control stability are given up here. There's 3 of them. There's capital T, which basically relates to the slope where the angle where the slope touches the ground surface at the top. F is just a dimensionless stability number, and phi is our other dimensionless number. And if we just suppose that a factor of safety of 1 applies when we have these 3 dimensionless groups, which satisfy these particular sets of soil properties. For the real case, a unit weight of 8.5, cohesion 16.8, chi-S, linear with depth, varying by that, and a surcharge. Now, using this equivalent method, we can go to a simple software like Slope W or Slide. Forget about all the unsaturated soil features. Instead, plug in an equivalent unit weight and equivalent cohesion. Look how they've changed from the initial values. Chi-S is now 0. In fact, all the pore pressures are 0 everywhere, and our surcharge is unchanged. And we can even put in an outrageous combination of properties. Here, the unit weight's nearly 79, the cohesion's 162, the surcharge has changed a lot. But all these 3 sets of numbers satisfy these 3 dimensionless quantities up here. And when you do your slope analysis, you get a factor of safety of 1, irrespective of which set of properties you use. And that's because those dimensionless groups are preserved, highlighting that this equivalent method is a perfectly physically acceptable way to capture the effects of partial saturation in these strength and stability problems. Now, back to the main topic. Why address the cone penetration test in unsaturated tailings? Well, large sections of a tailings storage facility are unsaturated. There might be sections deep within the structure where it is desiccated in the past and new tailings has been deposited on top. but it's just simply flowed over those dried out sections, and you still have these pockets of partial saturation. Or you can have obviously large desiccated regions above the phreatic surface as well. Very little research has been performed on how to interpret in situ tests of these materials, but I've spent the best part of 20 years looking how to handle the CPT when we push through unsaturated materials. We know suction influences the CPT results a lot and must be accounted for. And it's very important to account for suction in stability analyses and assessments, especially with tailings where, you know, the margins of safety are not high and the budgets required to retrofit and upgrade them are huge. So a little bit of factor of safety goes a long way financially, as well as from a risk point of view. So it's important to remove unnecessary conservatism to keep costs down and attain slightly higher factors of safety, but also it adds confidence to your analysis. And we all know that how confident you are in your parameters in your analysis dictates how low a factor of safety you might rely on when you present it to regulators. Now, one of the peculiar features, and one of the general features that I'll come back to a few times in this talk is shown here on the right. So if we've got essentially a static a groundwater system, we've got a phreatic surface through here. That is essentially the line where the pressure is zero. Everywhere below that, we've got a linearly increasing water pressure with depth. Slope gamma water, nothing unusual there. But immediately above that phreatic surface, we get a thing called capillary rise. Tailings, as I said earlier, has this optimal particle and pore size distribution, so it sucks water up into its structure and holds it there statically. The tailings remain saturated, but you've got a negative water pressure. So the rise of that section is our air entry or expulsion suction divided by the unit weight of water, and it can be around 7 or 8 meters in a tailings dam. I've seen evidence of that in the review work I do. You get real negative water pressures there, and practitioners need to account for that when they compute effective stresses and then interpret their CPT data and do all their stability analyses and so on, because at the moment they're not. And they're getting a little bit of misleading interpretation from their CPT results because of it, usually unsafe ones. And they're also missing an opportunity to enhance or increase the effective stress and strength inside those sections, which would add to the factor of safety later on. So this capillary rise is demonstrated in glass tubes as well. You can have essentially a static body of water in a large diameter tube here, but when you've got a really small tube diameter, through that capillary action, it pulls water up into that small diameter tube. So that the section in that tube above this sort of larger body on the right is in tension. There's a negative pressure in that water. And exactly the same thing here is happening inside the tailings dam. But the theoretical maximum is around 10 meters, and that's when you then get cavitation in your water. But there's impurities in the water, little bits of salt and grit that enables cavitation to occur sooner than the water rising by 10 meters. So I think the maximum is usually around 7 or 8 meters, although I might be wrong, but we need more data there. Now, as we go even further above that capillary rise section, air now has entered the tailings and it becomes partially saturated. The chi-S profile is now non-linear. It's not just an extension of this straight line towards the right and upwards, and now obeys quite a different set of laws depending on the infiltration, evaporation processes, and so on. Now let's go to some CBT observations. This is what we know for a clean sand. This is done a few decades ago now in a very basic calibration chamber, pushing cones into a sand in saturated and unsaturated states and so on. And you can see when the degree of saturation was around 0.1, your cone resistance is essentially double that for the saturated state. Very early evidence. We then go to Perth in Australia here, some field studies at the end of wet and dry seasons at a sand site where there's up to around 5% fines in that sand. At the end of wet season, all your CPT data is down here. At the end of the dry season, we've got a significant suction present in the sand, causing the cone resistance to double, more or less. This is some work we did at UNSW in our calibration chamber, looking at sand in saturated and unsaturated states. And again, over on the left, you can see how your cone resistance this outer sort of black line is much larger for that unsaturated state compared to what it is for the saturated one over here. It's particularly pronounced when your confining stress is very low, but it's still evident when your confining stress is up to 100 kPa, your unsaturated results are still markedly different from your saturated ones. We've done the same for a decomposed granite. This is very much like a tailings, a very well-graded sand silt mixture, perhaps a little bit coarser than tailings, but again, suction as it increases causes a rise in your cone resistance compared to the saturated value or the lower suction value. Now let's talk about drainage. This is one of the key learnings that I hope you take away from today. Look, when we push things into soils or tailings, or when they deform, we need to make some assumptions or statements around what's happening to the pore water pressures. Drained conditions will be great. It means that suction is constant, or even better, Chi-S is constant. So in other words, all the pore pressure parts and their contributions to the effective stress essentially don't change very much. But the most realistic scenario is that when we push a cone into the tailings or the soil, is that the moisture content is constant. It happens, fairly quickly. There's not enough time for water to drain in to or out of the tailings. So we analysed an expanding cavity in the soil to explore these different drainage conditions and what it does to the cavity wall pressure, which is analogous to the QC, the cone tip resistance. And we found a very useful discovery, that is that the constant Chi-S assumption is a pretty good approximation to the constant W condition. The errors are only always less than 30% and mostly, overwhelmingly, majority less than 10%. So it's a pretty close approximation without big sort of practical consequences, even though it's not perfectly true. Now, this is only really valid when our degree of saturation is quite small. And so you've got water being quite sort of isolated from the air is essentially vented to the atmosphere, or sufficiently large in volume that as the air compresses and doesn't expel to the atmosphere, the pressure changes don't cause a pronounced effect on the pore pressure changes in Chi-S that occur. Now, pardon me, this is all well and good from a general sort of drainage condition point of view. We can assume Chi-S is constant when we interpret our CPT data. But there's another effect of suction going on which we need to consider, and that's that suction hardening phenomenon. That is that shift of the isotropic compression line and strengthening of the soil and the tailings which occurs. And I'll show some results where suction hardening is clearly present compared to when it's not present at all. So this is an interpretation of the Sydney sand data. This sand doesn't really have a suction hardening. If it does, it's very, very small and can be ignored. And it means that all our saturated, unsaturated, and dry results essentially obey the same trends. And we can link cone resistance to our mean effective stress in a power law, for example, using this Boldy type expression. And that's all the data overlaid up here fitting that power law for two different relative densities. There's a mixture of saturated and unsaturated there, all agreeing the same relationships. We could alternatively use the state parameter approach of Bean, Jeffries and co-workers and adopt this sort of exponential law in terms of state parameter. And again, all your saturated and unsaturated data would obey the same trend. Now, these look very different, these two expressions, but they're actually essentially the same thing when you have drained conditions around a cone, and you can introduce your critical state parameters and sub in the expression for the state parameter, rearrange, and you can show that this power exponent on P is actually 1 minus lambda n when you go to this Bean-Jeffries type approach. Now, again, in this clean sand where there's no suction hardening, we can do some very powerful things with our cone results. We can relate two cone resistances at two different locations using just a ratio of the effective stresses which are present when raised to that power. So we can put in Chi-S parts to account, for the different suctions that might be present at two different locations. This is only true when the void ratios are the same. We can even interrelate dry, saturated, and unsaturated results. So here's a little example. If given some basic information about the test, about the Sydney sand, we can suppose that the cone resistance of 4 megapascals was obtained. Let's now suppose that the total stress, the mean total stress is 25 kPa and chi-s is also 25. So doing things properly, computing your effective stress will give you 50 kPa. Subbing in the various expressions, you get a relative density of 0.42, friction angle of 39 degrees, soil behavior type of 1.6 and so on. But if we ignore suction, we'll make no attempt to account for chi-s and incorrectly suppose our effective stress is our total stress, which is 25, we would overestimate our friction angle by 4 degrees, overestimate our relative density or underestimate our void ratio by quite a bit, and so on. So here, failing to account for suction leads to unsafe predictions as well. Another example of that Perth sand site, we can interrelate the cone resistances essentially at the end of wet and dry seasons. At the end of the wet season, I'm setting the pressures to 0. There's still a small suction present, but it's all at 0 or close to it compared to the end of the dry season. Interrelate them, and you can back calculate the chi-s value at the end of the dry season when you've got two sets of data side by side. Now, when we add fines, we start to get a very pronounced and unignorable suction hardening that we have to account for. And in an unsaturated state, we still get a nice power law relationship with our mean effective stress, but that relationship won't apply to when the soil is saturated. So we've got two different types of responses now around the cone. And that's due to the presence of suction hardening. It limits a little bit how we can then interrelate different sets of cone results. We can only interrelate them when both sets are from an unsaturated case, using a similar approach to Sydney sand, but we can't now mix in the saturated ones because of the different laws which apply. But there's some implications when we attempt to classify as well, using these well-known charts. The effects are not so pronounced for the Sydney sand, and I'll demonstrate that here. So the solid circle symbols are saturated. The open circle symbols are unsaturated, but correctly plotted. This is the Q term. Notice that there's an effective stress on the denominator here. So chi-s has been included in that properly. And I've redrawn the data, but when the chi-s part is assumed 0, or in other words, when the suction is ignored. You see the crosses now are wrong, but they're plotting slightly above what the open circles do. It's not a huge difference for this particular soil, but for other soils it can be. And this is a quartz marine sand. Here I've done the same things. Saturated results all nicely and correctly plotted down here with the black closed symbols, showing slightly dilative material bordering between 4 and 5. Now, in the unsaturated, suction was ignored, but look where the data's plotting. It's the same soil, but now it's plotting as a soil 6. It's looking to be very, very dilative, but we know that if it was to become wet for whatever reason, it would be down here where these black dots are, and you have something bordering like dilative, contractive. So you get things badly wrong with your classification. Okay, so now on to tailings. So I'd like to firstly acknowledge the tremendous team that have been involved here. There's 6 mining companies: Anglo American, BHP, Freeport, Macquarie, Newport, Newmont, Rio Tinto and Teck. There's 4 universities involved: West Australia, University of South Australia, University of Wollongong, and also my future fellowship funded by the Australian Research Council. So the key contributors on the CBT part of this project include my colleagues at USW, Yanzi, Wang and Tan Vo. but also a big team at UWA, Ioane Ayala, David Reed, and Andy Forey. So thanks to everybody for helping put this work together over the last 3 or 4 years. So I'm just going to focus on 2 tailings, a gold and a copper tailings. They happen to have almost identical particle size distributions, although they're from different continents and obviously very different rock types from ground up to extract the minerals. Look, tailings are usually fractal. I'm not going to get into the fractal side of things. It's a really neat mathematical pattern that exists. But if you take a double log plot of your particle size distribution rather than the linear log, you'll see something that's almost a straight line, certainly across the first sort of 2 or 3 log cycles. And the slope of that line is 3 minus our fractal dimension. So for this bottom one, which is the copper tailings, the power exponent is 0.39. So the fractal dimension is 3 minus 0.39, which is 2.61. And that is what we then use to capture the void ratio dependence of our water retention curve. Look, all the work that I'm going to present, or nearly all of it, is contained in this Geotechnique paper, which was accepted for publication just a couple of weeks ago. So it's a bit of a monster. It's nearly a 10,000 word paper. It's got tremendous amounts of data in it, and it's really shows some nice discoveries, which I'll highlight now. So critical state lines for the 2 tailings are shown here on the left. You can see how the saturated line's down here, and then for different values of suction, when normalized by the air expulsion ratio to make it dimensionless, you can see that there's a shift of that critical state line, sort of upwards and rotating a little bit. Now, you can put whatever lines you like through it, but I've just used the conventional sort of gamma lambda combination of parameters. Likewise for the copper tailings down here on the bottom. Notice that they all intercepted here 2000 kPa, here 5000 kPa. That's not anything significant. It's just that stress level is much larger than anything we have to deal with in this project. So, you know, but you could make them sort of taper off and not intercept if you wanted to. Here's friction angles plotted against state parameters at the beginning of shear. Saturated and unsaturated data more or less overlap. I'm sure there's some scatter, but at least we can now roughly relate a state parameter at the beginning of shear to some friction angle in excess of the critical state value. Here are the water retention curves. Again, notice the double log plane, degree of saturation versus a normalized suction. This means that there's no void ratio dependence in the presentations. It's always proper to non-dimensionalize your axes before you plot it in any scientific endeavor. And the best way to do that with the water retention curve is to using this expression for our air entry suction or air expulsion suction. You can use either, but with that void ratio dependence captured. Now, here's our CBT results that recovered from 2 calibration chambers, one at UNSW, one at UWA. Very different in design. One was very large, one was a miniature chamber using a miniature cone. And we've mixed together saturated and unsaturated data. The saturated is the solid signals, unsaturated hollow. And you can see that when normalized cone resistance plot against state parameter, we get more or less a unique relationship. Now, I must note, and it's very important, that the saturated tests in these silty tailings were performed very slowly, very slow cone penetrations. So we have drained conditions prevailing around the cone tip. If we were to use a normal cone size cone penetration velocity, we would have undrained conditions most probably. Likewise for the copper tailings here on the right, again, saturated and unsaturated data mixed together, more or less a unique relationship when plotted against state parameter. Now there's 3 extra results here with these crosses. These are for when this volume of air to total volume ratio is less than about 0.15. And I think that 0.15 volume ratio is a critical point where if you are larger than that, there is enough air in the pore space so that when you push the cone into the tailings behaves as though it's a drained material. The air may or may not be able to vent itself to the atmosphere. Even if it can't, it can compress in volume sufficiently during the cone penetration, because air is very compressible, so that the skeleton of the tailings can deform in a very similar way to what it would if it was a saturated drain test. So we're getting very similar material responses around the cone tip for both saturated and unsaturated cases. One where we have essentially free ability of the soil or the tailings particles to rearrange and behave as though they were drained. It's only when you have that much lower presence of air volume that the air pressure increases, it somewhat obstructs the way the tailings deforms, and you no longer have something similar to a drained state. You have sort of a pseudo unsaturated, undrained or partially drained situation. So those three data points, I don't know how to interpret those yet. That's the subject of ongoing work. But as long as we're above this threshold of 0.15, we can assume that we have pseudo-drained conditions all the time. So this is just a reiteration of that. This pseudo-drained condition prevails in all the unsaturated samples as long as that volume of air ratio is larger than 0.15. And that's because the deformation of the soil and the tailing skeleton is free, and it can essentially behave like it would if it was a drained material. And it's that deformation of the source or the tailing skeleton which controls the cone resistance and the strength the most. When we have that smaller air ratio, we've got something really complicated going on, and we don't know how to interpret that just yet. And we also know that the saturated ones were performed slowly, so we knew we had drain conditions. So now we go to the TSF from which those tailings samples were taken, and we look at real cone data. This is on the left here, the cone profiles with depth, two adjacent CPT tests. CPT2, the grey one, differed in that for a 1 metre length of penetration down here, we slowed the penetration velocity right down, so we had drained conditions. The black one everywhere else, we had undrained conditions. That was a standard penetration rate. Pore pressure, this second figure to the right now, let's look. So you can see that the CPT2 for the drained section had a pore pressure response very similar to what would be observed if we had a hydrostatic pore pressure. So this is our likely phreatic surface point here, but above that, the cone in both cases is measuring a negative water pressure. This is because it's still a saturated case, a saturated situation due to capillary rise. The cone is rightly trying to measure a negative water pressure, as it should. And it's only when you sort of go above another point even higher does the pore pressure readings essentially become zero, and the cone's not doing anything sensible at all. And that's because you've got a partially saturated region up here. So this is where our capillary rise section exists. Here it's only 1.8 meters, more or less. And you can start to demarcate the profile into these different regions. We can do some more things when we have two sets of cone velocities. We can interrelate them because we know the drained one also obeys this figure on the left, this relationship with this exponential power function of the state parameter. So we can then relate the undrained part of the penetration to the drained part and work out what the corresponding relationship would be for an undrained penetration. And that's what this dashed line shows here on the right. This black continuous line up here is our saturated drained case, which we know from our laboratory tests, and now we can interrelate that and find out what the undrained response and undrained relationship would be. And once we've established that, we can then apply that dashed line and that new relationship with those new parameters to all of the other undrained sections. These K and M terms and these B and Jeffreys type expressions are different for drained and undrained penetrations. That's not well known in the literature. It is an absolute fact. And this is one way that we can now interrelate them and use them one way or another to interpret the rest of our profile. We've recovered void ratios, state parameters, and so on. And we've also had some piston sample measurements of void ratios nearby. And you can see that those little grey vertical lines are those field measurements agreeing very nicely with our CBT obtained interpretations. This is now the copper tailings. Yeah, so this is all unsaturated. Now, this is QC on the left. Pore pressure, the next figure along, you can see there's some spikes in the pore pressure. We've probably got some layers there of nearly saturated or saturated with slimes or material inside the TSF, but then the pore pressure drops to 0 in other places. So it's where that pore pressure is essentially 0, we can treat the material as though it's drained because of the presence of air and the ability for the skeleton to deform, and then apply that relationship that we obtained earlier. And these are those void ratios that we get from it. And again, with block sample cut from nearby sections, the void ratios in those were very similar generally to what we recovered from that relationship, giving some confidence to all the other predictions as well. Now, all that requires a bit of knowledge around suction hardening. I must state that the state parameters in these figures are determined using that shifted critical state line, which depends on suction. To determine that requires quite a lot of laboratory testing using sophisticated equipment, which is generally not available to industry. So I'm very conscious that this pure, perfect interpretation is not easily done in practice. So instead, we can present the data using these types of charts. There's no reference to chi-S or suction hardening or critical state lines or anything inside these. I've normalized cone resistance against total mean stress. Here's your total mean stresses, the lines for different moisture contents. Now, these relationships are valid when we have an air ratio larger than 0.15 and when the hydraulic states on the water retention curves are at the midpoints of a scanning curve. So they're not on the main drying curve, they're not on the main wetting curve, they're exactly on a scanning curve at the midpoint between those two outer boundary lines. And the same is shown here on the right for the copper tailings. Now, you could recover these if you've got a huge amount of data from your tailings dam. You could essentially put all your dots on a graph here and then sort of draw some contour lines of best fit through it and try and shape it into forms that look a bit like this. And then you can go forward and apply those more generally across your structure. Now, this is a fairly key assumption, that the hydraulic state is at the midpoint of the scanning curve. And why am I assuming that? And I think during normal seasonal cycles of wetting and drying, it's really difficult for your hydraulic state to ever end up on the main drying curve or the main wetting curve. In fact, I think it takes very unusual or prolonged wetting or drying, so extreme floods or droughts, to actually cause that to happen. So during normal operations, I don't think you ever end up on your main wetting or drying curve. You're always hovering on a scanning curve, zipping back and forth between your main wetting and drying, never actually reaching it. There's a little bit of direct evidence of this as well. There's not a huge amount of evidence. I think it's something that we need to get on top of as a discipline to help the uptake of unsaturated soil mechanics in practice. But we had 2 years of monitoring data in New Zealand on a soil slope. And these outer black lines are laboratory determined water retention curves. And these grey symbols are the field measured values during wetting and drying over a 2-year period. And you can see that they always essentially just zigzagged back and forth on the same scanning curve. That you will never saturate the soil to the extent that the degree of saturation becomes 1, nor do you ever dry it out enough so that you move further down the main drying curve. Look, I won't go through this. I'll let you read that in your own time. I'll just finish with a little bit of additional data related to instability and post-liquefaction strength. These are some triaxial tests on a tailings. Degrees of saturation around that 0.63 to 0.75 mark. Fairly loose, but not extraordinarily loose. You can get up to void ratios of 1 without any trouble, so there's still a bit of looseness to go. But look at the responses that you observe when you close the valves in your triaxial system. So you trap the air and the water in the pore space, it can't enter or exit, right? So we have a closed constant mass system. We can calculate the pore pressure changes, the pore air and pore water, compute chi-s, so we can calculate our effective stress properly. But you're getting responses that look a bit like you see for a saturated drain material, sort of increase in strength and then some sort of softening as you approach a critical state. Obviously, there's the ability to this materials to compress in volume because the air deforms. Air is very, very compressible compared to solid and water. And we can start to pick off things like collapse lines and try and relate it to degree of saturation, for example. This is well known for those who deal with static liquefaction generally. If your stress state's down here, you've probably got a stable material, but if for some reason your load path sends you to the right, so you cross over these collapse lines, you've got a real potential for liquefaction and a massive strength reduction. But those collapse lines now depend on the degree of saturation, and that's what these numbers in brackets represent. There's a load path dependency here. These collapse lines I've drawn are for the pure triaxial load path, which your valves have been closed the whole time. But that's not what happens in the field necessarily. You can have a stress state that starts over here somewhere, and then you've got slow pore pressure reductions causing you to move leftwards due to your pore pressure changes and increases, while your deviatoric stress is essentially constant. So we know that for that particular load path, you get collapse with drawn in the inset at these black lines, which is much sooner than what you would see for the triaxial load paths, which are these sort of straight lines drawn up here. So there's a bit of work to do here to understand that load path dependence, but it looks like we can start to apply some of the basic ideas for saturated soils to unsaturated ones as well, once we get on top of that load path influence. We can also start to plot things like post-liquefaction strength ratio as a function of the initial state parameter. There's a little bit going on here, but these square symbols are experimental measurements. This line through here is a model prediction for the degree of saturation of 0.65. This dotted one through here is when the degree of saturation is 0.85 and so on. But again, this is plotted in terms of the state parameter, which accounts for that suction hardening effect, which, like I said earlier, might not be something industry can do. So we can also plot it in terms of modified state parameter, which is really the state parameter that would be determined by ignoring suction and relying just on the saturated critical state line, something industry can do. And we can come up with some alternate charts there. And here, again, model simulation 0.65 through here, and some dots for lab data and so on. So work in progress, but this is where we're heading with that incorporation of suction into that post-liquefaction strength. Now, some of the big mining companies are very aware that it only takes a degree of saturation of 0.8 or something for liquefaction to still be possible. And they're asking their consultants to now deal with that in their designs. The consultants generally don't know how. I don't know how. No one does, but we're now making some steps towards helping them so we can deal with that. Anyway, here's a neat summary for the practitioner, so please share this around. It relates to that sort of ground pressure system set up inside the tailings, saturated below the phreatic, capillary rise immediately above. So in that capillary rise section and below, we can use saturated soil mechanics but we have to account for the negative water pressure which is present in that saturated capillary rise section. So that negative water pressure appears in the denominator of a CPT interpretation. It appears in the denominator of a strength ratio. So you really have to account for it. Otherwise, you're going to get misleading, interpretations from your CPT or a misleading undrained strength in your stability analysis and so on. Okay. We can still apply Skempton's A parameter, B bar, and do all the usual things. Above, near the top, where we've got that high air ratio, larger than 0.15, we can use either unsaturated soil mechanics or this equivalent method in total stresses. But we need that chi-S profile to get our equivalent cohesion and unit weight. The soil, the tailings will behave as pseudo-drained because there's enough air present so that it can deform whatever the loading rate so that that chi-S is essentially constant. But there's a large section where we still don't quite know what to do, and that is when that volume of air ratio is less than about 0.15. Here we could use unsaturated soil mechanics or perhaps a total stress analysis, and use some sort of total stress strength parameters, CT, phi T, but we have to make sure they're recovered from essentially the same load path that we're expecting to experience in the field, because those parameters are very much load path dependent. So we need to be careful there. This is probably the best we can do right now. Look, I threw this slide in knowing there's a large industry contingent. So this is the mistakes that I'm seeing in industry in Australia. Look, a lot of companies are now using unsaturated soil mechanics in infrastructure designs, and this is following some recent policy changes by our government departments. So there's a frenzy of people doing it, but they're still making mistakes. So I put this here so you don't make the same mistakes when you go and have a go. The good things universities are doing, they're engaging universities to determine water retention curves. Great. They can go forward and use strength stability using equivalent cohesion. They probably should use an equivalent unit weight as well, but it has, to be honest, a secondary influence compared to the equivalent cohesion. So most of it is captured through that cohesion. And they're adopting this influence, suction influence parameter. It's in the Australian standards, which is basically a shrink swell parameter for vertical movement, but they're exploiting its connection to elasticity to predict deformations in multiple directions. But the mistakes are many. So let's go through those. People assume total suction contributes to strength, irrespective of the individual contributions of matrix and osmotic components. In some of Australia's soils, there's a big osmotic component due to the presence of the salt. And the Australian standards doesn't really differentiate between the two, which is, I think, quite misleading. So just stick to matrix suction as much as you can. Generally, the osmotic part doesn't do much to the mechanical behavior. It does a little bit, and we don't really know how much, but it's the matrix part that does most of the strength changes. People are generally overlooking hydraulic hysteresis. One of the questioners in Hariano's talk pointed this out. People too often assume hydraulic state lays on the main drying curve when they're designing for a wetting event, but this is not what you should be doing. You need to use that wetting curve. People don't realise suction needs to be scaled by multiplier chi or tan phi b before they incorporate it into a strength. And, therefore they might presume a suction of 100 or 1,000 kilopascals in a clean rock fill sounds impressive and large, therefore it must provide a lot of strength gain, when the fact is chi or tan phi b is essentially zero, and that suction does virtually nothing. These devices people use to measure suction, like the MPS6 or the Terrace, I think they're fine as long as the material, the tailings and soil is undergoing drying. And there's only a calibration curve for those which is relevant to a drying process. So you can't use them if your soil is getting wet. In fact, all the wetting data needs to be put in the bin. You have no way to deal with it. And I even think that drying immediately following a wetting event can't be used either. And that's because the ceramics inside those have their own hydraulic hysteresis, and the calibration curve doesn't correspond to the scanning part of that hydraulic hysteresis. It only corresponds to the main drying part of those devices. So we need to throw that in the bin as well. So you'll only get about a third of your data that's useful when you measure these. when you use suction measuring with these devices. We've got to be careful with our terminology. To see too many practitioners would use words like undrained shear strength when interpreting unsaturated soils. I mean, has no relevance. This is like a constant volume saturated phenomenon. It's got nothing to do with unsaturated soils. Be careful with piezometers, especially if you embed them in an unsaturated soil initially. There might be enough suction that it sucks the water out of the tip of those piezometers straight away. So when the water table rises later on, the piezometer tip's unsaturated and has no ability to saturate properly and give a reliable reading. Too often people are ignoring the capillary rise above the phreatic surface and the enhancements it gives to effective stress. Yeah, so they're the main ones. Good luck with it all. And look, here's my conclusions. Strength stability, use the equivalent method, that's fine when your cohesion suction increase linear depth, at least approximately. That's the way to go, and you can resort to commercial software without using the inbuilt unsaturated soil features. Yeah, look, the rest is there. Large air ratio 0.15 or more. You can use this equivalent concept quite well. Chi-S won't change much, whatever the deformation type. But when your air ratio is less than 0.15, we've got a really complicated system. We don't really know what's going on there. You could resort to a total stress type analysis as long as your load path is similar to what you have in the field. But look, yeah, that's all I've really got to say. Good luck, and happy to answer any questions. Okay, so if they're contractive when partially saturated, you've got real problems. Normally the opposite is if they're unsaturated, they tend to look dilative, even though when they get saturated later on, they're very contractive. So for something to start off as looking contractive while also being partially saturated, it's going to be extraordinarily unstable when it becomes wet later on. And in fact, you'll probably get instabilities as soon as the water table rises and saturates the material. You'll get volumetric collapse and all sorts of things going on. Yeah, so yeah, what strength do you put on it? Something very, very small. It'll be around the lowest that's ever been observed historically, around that 0.06 ratio mark. So yeah, if they're looking contractive when it's partially saturated, I'm in all sorts of trouble there. That's a good question. So there was about 2.8 meters of penetration in that unsaturated region. So look, I don't know the details of exactly what they did on site, but these were reliable contractors. I'm pretty sure they would have been using glycerine or something equivalent in the pore fluid in the piezometer tip, plus the rubber protection that we put over it. Now it will desaturate only really through cavitation, and for that to happen, you would need at least like 100 kilopascals of suction for it to occur. And that level of suction may or may not have been present. I'm guessing, you know, with all those other protective measures, by the time the rubber breaks away and so on, you probably have the tip exposed to a suction that's not 100 kilopascals, so it won't desaturate. The fluid in the tip can hold 100 kilopascals of suction before it begins to desaturate. Yeah, so look, yeah, this is about the critical state line in the QP plane. I didn't mention it, but generally, as long as you put your suction into the effective stress P properly, then you see the same critical state line in that plane, the same M slope for both saturated and unsaturated conditions. Sure, that there might be small differences and here and there you can argue about, but practically speaking, they're the same line for both saturated and unsaturated conditions. Yeah, so look, there's a lot of data that proves this, to the point where we don't, it's not even a controversial point of discussion anymore. So it's pretty well accepted.